Hi everyone, my name is, I don't see the slide here, okay. My name is Emanuela Marasco, and I'm presenting this work that I did with Alex and Keleigh, she's here. Both are just undergraduate students, so we were at the University of Charlotte, North Carolina, last summer. That's why we are presenting this paper. And the focus is on automatic improvement of interoperability between optical fingerprint sensors. So device diversity does induce variations in the images. We want, of course, that the representation of the identity is like invariant to raw data. But we did notice differences even visually, as we can see in the figure here, due to nonlinear deformation mainly, related to, for example, impression type, intensity, and how the user interact with the sensor, different devices. Variations in image quality. So in previous papers, we did publish some histograms about how NFIQ changes across different devices. We are talking about the same technology, optical only, and the matching features, so minutia points that are translated and rotated. So we now focus on capturing variations in texture. So device diversity does induce variation in textures. And so this we want to study how well we can capture patterns in different images. We can see here like how different are images pertaining to the same subject, so same finger, when we use different devices with same characteristics, even locally, right? So the goal of this research, of course, we want to match in cross-sensor scenarios with the same accuracy as in intra-device. We are using optical sensors that are very accurate, so they are used now, deployed in high security level applications like US Visit. We have cross-match devices. So we can see that we are considering same manufacturer, different models, and also different manufacturers all together, all possible combinations. And we want to match two fingerprints acquired using different devices. We can see here distribution of match scores. This is the first one intra-device. So we have genuine are very well separated from the imposter scores. They work very well. But in cross-sensor, this overlap area, of course, is wider. And this is causing an increase of false rejection rate. So this is what we want to improve. The baseline. Again, more details. We have very good performance in intra-device. This is the cross-match, the Guardian. Again, intra-device until we consider the blue curve. These are DT curves, where we combine 4 different optical devices certified by FBI, and with tempering card as well, so same subject, and here we have all possible combinations. So this is the challenge that we are solving. We want to improve this error rate. We can see that in like for a low false acceptance rate, the false rejection does increase, and it is almost close to 6%, which is not acceptable. This is a general architecture of the process that we are of our approach. So we have the training phase. And we can see we add an extra image processing to the input images. We do have the traditional matcher here. So we do use existing matching because they are mainly designed to operate on fingerprint acquired using same sensor. But what we do, in order to mitigate the cross-sensor scenario performance, we have an additional feature extraction step. And then selection after concatenation. Then we want to, of course, use these features interoperability set to train a classifier, and this classifier will be making a decision in cross-sensor scenarios. which are the features that we are studying. So in previous work, we did exploit match score. So we used identics matcher, but we are evaluating this work also with different matchers. So currently, my students are working on VeriFinger. So this is a pairwise feature. We have image quality used as a single feature, so we have two values, two images, two values. And FAQ version 1, we are extracting, of course, version 2. Alignment parameters, so the alignment does impact, so we wanted to use the output of the Howe transform, which is actually, the goal is to compensate linear transformation, while we are talking about non-linear deformation to be mitigated, and then the image gradient, so we consider the difference. So this is the preliminary feature set that we evaluated, and then in this specific paper we add more details about differences in texture. So specifically, we present results by combining local binary pattern and local phase quantization, histograms. Again, some more details how we concatenate it. We do like feature fusion. And so again, this is a case study where we use two different sensors for gallery and probe. We use the traditional matcher, so we obtain both quality and match score on the side, and in parallel we perform XR processing, so LBP, LPQ, interoperability features concatenated with quality match score. We have trained a random forest and then evaluated the verification performance. Local binary pattern, so it is a very well-known, powerful tool to analyze the texture. So robust to monotonic gray level changes, simple computation, robust to rotated features. So we have an example where we apply to fingerprint image. So the window of analyzed is divided in cells. So we have the central pixel value compared to the neighborhood, and it's 0 if it's higher the value, otherwise 1. So we can build our 8-bit string, and we use in this work uniform local binary pattern. So we just consider a subset of all the possible combinations of the pattern, and we of course consider the histograms as features. An example where we can see how well LBP can capture differences between different devices. So we are talking about same subject, so the identity, and then different sensors. So we are looking for tools where the identity is isolated with respect to the sensor noise, right? And then local phase quantization, it is robust to image blurring, so this does help to isolate the identity from sensor noise. So again, the process is a local texture analysis, so we do have short-term Fourier transform, and quantization, binarization, and again we extract histograms, so our feature are histograms. We are, of course, studying more about this aspect, and one limitation may be due to the assumption that in this descriptor are related to the blur function, right? So this is assumed to be centrally symmetric, which may not be the best for nonlinear variations induced by sensors. The data, so we, at GMU, so we got released data from West Virginia University. This is a collection of, the database is large, so we have all the 10 fingerprint, but for this study we just used the right index. These are rolled fingerprints, so very good data. For optical sensors and temprint card, we do have like almost 500 subjects, the same for different sensors. These are an example of the images, so same finger, very different, very challenging for the matcher. Details about the sensor, so same technology, same resolution, 500 dpi, almost same image size in all the cases. Just one sensor has like smaller area, acquisition area, so this can give an idea how robust this approach is with respect to smaller capture areas. And this is the data. So experiments, so we did apply some dimensionality reduction before training. And then we used random forest classifier, random partitions 10 times. We divided the subset, training, validation, and test, so that the subjects are mutually exclusive. And then another extension will be a partial training with respect to the device. We didn't do yet, but we are working on it. Some results, some features. So the gradient difference is also in this evaluation a powerful tool to discriminate. And then we are talking about gradient difference by device pair that we can see. So variability is higher for cross-sensor scenarios. We also have the same feature with respect to the classes, because at the end we are talking about verification, so the match and non-match classes. We can see the difference of the median for matches is very different than non-match cases. We have some details about the classifier. So we, of course, 10 runs. These are results for false acceptance rate 0.01%. The baseline, very high false rejection rate. The preliminary set of feature does improve by 1.7, so we still have a big improvement. This is a previous paper last year that we presented, still very good performance with a more complex random forest here. With this approach, we do obtain a slightly improvement, but the main thing is the simplification of the method with RICA applied to the LBP, LPQ separated. So if we fuse the bot, we don't improve. Mainly LPQ was the best descriptor in this case. And we can see also that the standard deviation is not high as in the past evaluations. The results, so we have now results for all possible thresholds. We compare, of course, the baselines far away, and we can actually reduce with RICA LPQ very well. So we go down to 4%, a little bit more than that. So conclusion, we did obtain improvement with the local descriptors. So in particular, LPQ was effective, variant to blurring. The fusion does not help in this case of both. And now what we want to do is extension. So we have a pending IRB at GMU because we want to perform multi-sensor data collection where we do have more samples per subject, per device, because here we only have 2 samples. So we need to study also the variability in the same device. So we need like 10, 20 samples, same identity, same device as well. So this is what we are starting there. And also I'm studying the equivalence between RICA and autoencoder. So currently I have a student we are working on denosing autoencoder, formulating these interoperability issues as assuming there is a specific sensor with high quality images, it's a guardian, so cross match. So we assume that as the ideal representation of the identity through fingerprint, right? And then all the other devices that present variations are a noisy version of the ideal one, so that we can, the idea is to generate robust fingerprint images in order to have a better interoperability between optical fingerprint sensors. Thank you to the reviewers. We did get very good feedback, so these new directions are also because they suggested that, and also to NSF because of the program which allows to fund for summers students. They are just undergraduates, so they can spend the summer to be, involved in research. And so Keleigh is here. She did it last summer, and I think she will also do this year. Probably she's a very good student. Alex is not here because he didn't want to skip classes. Very good student. So thank you so much. Thank you. Any questions?
All right. Let's thank the speaker. All right. We have time for a question. Or Ben?
Suggestion?
Yeah. So if I understood, you were using the image quality as a feature for both the program and the
Yes, exactly. Yes.
And
So one value per POM.
Yeah. So I guess it's very common that you'd have a more degraded quality fingerprint. So I guess how do you see that generalizing to I guess other conditions? I mean,
Well,
I guess the sensors that you tested here was you had fixed sensors, but I guess
yes, here we found out. So there is a paper that we already. I didn't actually present the part on quality because we did have a paper in BETAS 2013. So I can send you some references. We do have like histograms about the values. So and we did find that as general trend there are like some sensors, they do have like higher quality, better quality compared to the others with respect to NFIQ V1. We are also doing the same with the new version of it. So we have actually more details because it's continuous, the output for NFIQ2. So in this case, Guardian was providing better quality images. And this does help in information fusion. But of course, here we also have, it's not alone, I mean, not only image quality, we have Fourier domain as well. So we did analyze and we extracted features from Fourier domain. So this is, of course, incorporated in that information that we are using, right? So.
Okay, great. We're ahead of time, so I think we have a texted question from the audience. How well does this method translate to touchless cross sensors?
Yes, I don't have, since I didn't evaluate and I didn't work, I don't say anything.
But with regards to the shape and the geometry captured by, you would probably have to do different pre-processing.
Yes. Okay. So I think the problem should be reformulated. So
right.
Yes, I don't think we can. So here we still have some work to do. Of course, the idea is with smaller images as well. And mainly, we do want to do the evaluation with the unknown devices in testing. This is not the case. For now, we are in, so subjects are mutually exclusive, but not devices. So I think here we want to see how well this system how well it's scalable in the presence of a new sensor, right? So unseen in training, and we started to do this experiment, and it did. So the performance did drop that much. So this I can say, but I cannot say things I don't know.
Thank you very much.
Thank you.
Thank the speaker again. So we have last talk. We have. Let me pull it up on my. It's.
Are you using? Yeah, actually, I changed it.